Hello and welcome to a repair video. I got this unit from our local eBay equivalent. This is a Kenwood TM-D700. It's a ham radio transceiver, a radio that can receive and transmit on 2 ham radio bands. I got this because it can send and receive data packets. But don't get excited about that. This is a fairly low-speed way of exchanging position beacons and weather information and things like that. And in fact, I don't know much at all about this technology, but I thought it would be interesting to look at. So this unit sort of came in handy because I didn't want to pay a lot of money just to be able to look at sending data packets and APRS and these kinds of things, but because it's faulty, I was able to get it under $200, which would be a bargain if this unit was operational. But for a broken unit, I don't know anyway. We'll see whether I can repair this. It was advertised as having a faulty display, but the rest of the unit apparently is fully operational. And from the description, it wasn't clear whether by faulty display they mean that the LCD inside of this head unit doesn't work, or whether the whole head unit does not work. And so I had to sort of buy this blindly, but it was clear from the picture that the LCD itself was not mechanically broken, which is sort of important because if the glass is shattered or broken, this you obviously cannot repair without replacing the LCD, and I didn't want to do that. So I could rule that out, and also there is a service manual available online for this unit, which might come in handy. So the goal of this video is to repair the unit, and let me power it on to show you what's broken. Essentially, I have now this unit connected to a 13.8 volt supply. It's coming from my lab supply because I want to be able to monitor current consumption and things like that. And I also hooked it up to a 50 ohms dummy load, the antenna port, because I don't want to destroy the output stage of the radio just in case this guy decides to transmit. So I could also have hooked up an antenna, but I like to keep things controlled if I'm not sure what's going to happen, hence the dummy load. Okay, so power is there. Now, if I try to power this on, just nothing happens, okay? Now, I noticed that if I wiggle around the head unit, now of course I won't be able to show this on camera, but sometimes the display comes on briefly, but in that case it's all black, and of course I'm not able to reproduce this on camera. But you've got to trust me on that. The whole thing is black for maybe half a second. Sometimes there is just one line. It's really hard to reproduce. I was able to get the speaker on once, but clearly something is broken here. Actually, I'm not sure whether this was plugged in while I was wiggling around, but it just fell off. So maybe if I... No. Now it did it. I'm not sure whether you were able to see this on camera, but the display was black for 1/10 of a second or something. So as I plugged it in, oh, it did it again. So there is something wrong, obviously, and now the first step is to decide whether the problem is likely to be inside the head unit or inside the base unit. And I think I'm going to open up the head unit first, have a good look at it, measure a few voltages just to make sure that everything is fine. And then if I'm not able to find a problem inside the head unit, I'll move to the base unit and have a look there. One motivation for this is essentially when I'm wiggling with that unit here, and and things kind of change on the display, this points towards a problem inside there as opposed to the base unit. And also this is, if I looked at the service manual already, and the insides of this is super easy, it's very simple. So fixing a problem in there is much easier than fixing a problem in the base unit. So I'll try my luck with the remote head first. So let me open this up, and then we'll have a look at what's inside and do a few measurements to make sure everything is fine. Okay, so I opened up the head unit, and as I said before, the internals are not that complicated. It might look intimidating, but we'll have a quick look. First of all, through this cable is used for several things. First, this has a 9.5 volts supply rail in there. So two wires in there are for 9.5 volts and the ground return path. Then there is two more wires, and these are for communications between the head unit and the base unit. For example, when you change the frequency, this guy has to tell the base unit, hey, you have to change your frequency, you know, so things like that. So there is a total of 4 wires in there, a ground, a 9.5 volts supply rail, and then a transmit and a receive line for communications between the two units. This has nothing to do with actually transmitting or receiving on the radio. This is transmitting from the head unit to the base station for, you know, commands and things like that. So the 9.5 volts are used for two things. One is to power a bunch of LEDs. These are low side switched from the CPU, and we're not going to care about those. And then the 9.5 volts also go through this track here to a 5 volts regulator. There is also a diode, so it actually comes from the connector through the diode to the regulator. This is a 5 volts regulator. I know that, I actually know all of that from the service manual, but you can also read that this is a 7805 regulator, so there is no surprise there. 5 volts regulator, and this is powering then the CPU, and this is a flash ROM, probably just contains the program that is run by this CPU, as well as a crystal to generate the CPU clock. And the rest are just transistors for switching and, you know, pushing buttons and things like that. And there is also a flat flex here going to the display, as well as 2 riser boards here for potentiometers. And an encoder here. This has all to do with the controls on the front of the unit, and I don't care about that at all. I see 2 things that could fail here. One is something to do with the power conditioning here around this regulator here, and the other one is the flat flex that goes to the LCD. These are really prone to you know, getting loose or disconnected or breaking. So that's the 2 things I will focus on now. And I'll start by checking the voltage, because the service manual tells me that I'm supposed to get 9.5 volts here on the input of the regulator, or actually it's more like 9 volts, because there is this diode here, and this diode is causing a 0.7 volts drop, but whatever. So I'm going to check whether I get that voltage. Okay, so I've arranged things such that you can see both my multimeter as well as the remote head unit. And as I said, the goal is just to check whether we get these 9.5 or 9 volts here at the remote head unit. And I know that this tap here of the regulator is ground, so I have easy access to ground here, and then I'm just going to measure the voltage at the anode of that diode with respect to ground, and at the cathode of the diode with respect to ground, and check what I get. So I will first turn on the power supply, and then grab my probes here and measure from here to here, and this gives something like okay, essentially 0. So there is no voltage here whatsoever. No. Okay, so let me turn off the supply here. So this means that I don't even have to bother to check anything behind that regulator, because I think the problem is somewhere before. So I will detach the I just detached that connection cable again, and just as another quick check, I'm going to measure whether there is a short at that input. So that's 900K and 600K. So in theory it is possible that when this guy turns on, some silicon junction gets turned on and then the input is shorted. But that's kind of unlikely. So what I'm going to do next is I'll go and grab the base unit and check whether I have these 9 volts here. What I cannot do is measure whether the 9 volts are present when the head unit is disconnected. Because I'm measuring inside of the unit, so of course when it's disconnected I'd like to know whether I've got the 9 volts here, but these connectors are extremely annoying to measure because you're never really sure whether you're making contact with the connector. So I'm going to open up the base unit and hopefully get easy access to the connector here. I wanted to open it up anyway to have a quick look, so no problem there. So let me open that up and we'll take that measurement. By the way, interestingly, let me see if I can pull this. Okay, interestingly, the seal here has been broken already. So I really hope that nobody opened it up without knowing what they were doing and messed around inside the unit. But let me turn off the camera, open it up, and we'll have a look. Great, so I opened up the base unit. Was fairly easy, couple of screws. Then you can take off these, the casing essentially, and remove the plastic cover of the front. And then I just put them back in order to provide at least a little bit of protection. So that is the connector that we're interested in here, and I do apologize if this is hard to see. But there is 6 solder joints here. So in fact, the first and the last pin of the jack here are not used. And then 6 minus 2 is 4. So that guy here is or should be at least the 9.5 volts power. That one should be ground. And then there is 2 more for transmit and receive. So I'm going to try to measure the 9.4, it's 9.5 actually, 9.5 volts there, and I'll connect this guy, this goes to the common of my multimeter, and I'll just hook this up to the case where there is a metallic surface, and that just allows me to handle 1 probe instead of 2, which hopefully will make things easier. And I will zoom out just a little bit in order for you to also see the multimeter. Apply power to the device and then take my measurement. Should be here. Okay, cool. So that is 9.6 volts, 9.5. That's about right. So next I will connect the remote head unit. In fact, let me do this first. Let me first, just to be on the safe side, connect the cable on one end. So the end that goes to the remote head is currently disconnected. So is the head, the connector that goes to the base unit, and I'll just measure the 9.5 volts again while plugging this in. Now in theory nothing should change, and okay, well, wonderful. So I feel a bit sorry for the people who sold me the radio for so little money. If you don't know what's going on, pause the video right now and think about it for a second, and we'll resume in a second trying to figure out what just happened. Okay, so chances are that there is just a short inside of the cable, shorting out the power rail, and of course then the voltage drops and the head unit doesn't power on. So to check that, despite of what I said before, I'm trying to measure whether there is a short, but that's exactly the reason I didn't want to do that. This is highly annoying. Okay. This guy is completely shorted out. So let me try to get a replacement cable, and maybe that's all that is needed to get the unit back into a working state. Okay, great. So I just had an interesting chat with my favorite radio gear supplier, and he informed me that the cable that I'm trying to replace is actually very hard to get. Reason for that is that it's not really a standard cable. The connectors are standardized. If you look closely, you see here there is 4 conductors, and on the other side 4 conductors as well, although one is a bit thinner than the other one, like this. So this one is actually called a 4P4C connector because it has 4 positions and 4 electrical conductors. And this one is called a 6P4C connector because it has 6 positions just by the width of it. You could put more conductors in there, but there is only 4. That's why it's called 6P4C connector. You might compare this to, let's say, something that is used for Ethernet. This is not an Ethernet cable, but anyway, the dimensions of the connector are the same. This is an 8P8C connector because it's got 8 positions and all of them are filled with a conductor. So anyway, there is that. So there is no standard cable with a 4P4C connector on one end and a 6P4C connector on the other end. But what you can get is, you can get, for example, this, which is one cable that has 4P4C on both ends. So my plan is to take this cable that I just bought and to cut off one end and to put on one of these connectors here, which is a 6P4C, I guess. Yeah, 6P4C connector, and if I get the wiring right, that will give me a replacement cable that should work. There is one problem though. To do this properly, you need a crimp tool. For example, this is a crimp tool that I use for Ethernet. So the idea here is that you plug in your uncrimped cable with a connector here, and then by squeezing the crimp tool, there is these indents here that push down a metal plate inside the connector. I'm not sure whether you can see that. And as this metal plate is pushed down, the conductor is pierced, establishing a connection. So that's the proper way to do that. But unfortunately, if I use my crimp tool, that is for 6 or actually for 8 conductors, I cannot use this crimp tool with the housings that I bought here because it's just not going to work, because the outer 2 notches here will hit the plastic, and I won't be able to push down the remaining ones. So I'm going to do something fairly horrible. I will take the connector, cut off one end of the cable, and then try to use a screwdriver to push down these metal plates in here. Now that's I'm very sorry for that. That's really not the way you should do that, but I don't want to spend the money for a crimp tool that I will never ever use again. So in case that works, I will at some later point in time, like fix the cable properly with the crimp tool that I borrowed from somewhere. Okay, I'm done with that cable, and trust me, this was a horrible experience. I'm not even going to show you the result, but please just, if you ever consider doing this, do it properly. I told you that it was a good idea. If you decide to ignore my advice, please at least do not use a hammer to hammer in the little plates, because otherwise you might hurt yourself. So yeah, just do it properly, okay? In any case, let's repeat the experiment. I'm currently measuring the 9.6 volts at the connector on the base. I'm powering this unit. This unit is powered up, and I'm just using a little grabber here to make the measurement a little bit easier for me. So the first thing I'm going to do is I'm going to plug in the cable at the base unit as I did before. Remember that this was the step that failed. So let's plug this in. Okay, so there is no short in that cable. Note that this is different from what we observed before with the faulty cable. And now let's take the other end of that cable and plug it into the remote unit. And okay, so this is not working. This is dropping to 3 volts. If I try to power it on, no. And it's recovering. Okay, so apparently the broken cable was an issue, but something else is broken too. And there's really 2 things I can think of right now. Either there is a short inside the remote unit. I tried to verify that quickly before, and there doesn't appear to be a short, but as I said, as this power is on, it might activate something that creates that short. So this is not off the table yet. It's just kind of unlikely. Or the circuitry that generates the 9.6 volts inside the base unit is faulty. And this is quite likely because we had a shorted power rail here, and this might have damaged the circuitry that regulates the 9.6 volts. So I'm going to try and investigate that first, and if this seems fine, I'll get back to the remote unit. So give me a second to set up a little experiment here, and then we're gonna check that hypothesis. Okay, so I changed the setup a little bit. Essentially everything is still the same, but instead of the Fluke multimeter, I connected this dummy load here. In case you haven't seen my video on this dummy load, this unit essentially allows you to pull a set current. So let's say you want to pull 10 milliamps, you set 10 milliamps, and it's going to pull 10 milliamps. So this is ideal for testing power supplies and debugging power supplies. Now, what I will do is, first, now the load is disconnected, it's not drawing any current, and I can read that there is a 9.5 volts across these 2 terminals, which are connected as before. So that's exactly as it was before. We have 9.5 volts when there is no load. Now if I try to draw some current and the power supply in here works, and by power supply I essentially mean the circuitry that generates the 9.5 volts. Now if that works, I should be able to draw 10 milliamps no problem, because that's a fairly low current. So in all circumstances the power supply should be able to provide these 10 milliamps at 9.5 volts. However, if the voltage drops in exactly the same way that it dropped when I connected the remote unit, I will know that there is a problem with the power supply in there. However, if I'm able to draw, let's say 100 milliamps or 150, 200 milliamps, there won't be any problem with the power supply in here, and I should look at the remote unit for any further failures. So let's try and do that. And by the way, just as a side note, all the things that I complained about the software in my review of this unit were pretty much fixed in a firmware upgrade, so and that's really cool. Anyway, so let me draw, let's say 10 milliamps, and I want you to observe the voltage that the power supply inside of the base unit is providing. So now I'm not pulling anything, and now I'm pulling 10 milliamps, and indeed the voltage dropped to essentially 0 volts. So the power supply in here is not able to provide 10 milliamps at 9.5 volts, which for sure it should be able to do. So I'm sure that there is a problem with the power supply in here. Now if I disconnect the load, the voltage should rise again. Yeah, right, and it's rising back to the 9.5 volts we had before. And if I connect the load again, it should drop once more, which in fact it does. So what I will do next is I will have a look at the service manual once more, try to figure out what circuitry is responsible for generating these 9.5 volts, try to find that inside the unit, have a visual inspection, and talk a little bit about the circuitry maybe, and try to figure out what's wrong. Okay, so I had a look at the service manual and also at the unit itself, and I discovered something that looks a little bit weird. If you look at this section here, this is filming through the hole through which the loudspeaker is inserted. I'm really sorry that I can't zoom in any further with this camera, although I will try my best to include a large magnification picture that I will take with a USB microscope for you to see exactly what's going on. But also here, if I put some light on there, you can see that there is a transistor here at the very edge, and this transistor has a blowout hole. You can see also a diode, some more transistor and capacitors. We'll talk about that. If I tilt the unit a little bit more, you'll even see some soot or something here on the chassis. You see that brown stain here. Clearly that transistor is blown out, and I'm fairly confident that this is actually the circuitry that is responsible for generating that 9.5 volts rate, and I'm going to tell you why. Although I don't want to discuss the whole circuit, because that's not the point of this video, although the circuit is fairly interesting. Essentially, this is the circuit, and I pretty much copied this from the service manual. So we're getting some input voltage here. That's probably 12.5 volts, 13 volts, whatever. I actually want to measure that, but the first part of this circuit here is a Zener diode, an 18 volt Zener diode that connects to the base of a transistor. Now this is not very important. That's essentially just some circuitry to prevent or actually to turn off the power supply when there is a massive voltage overload at the input, because essentially this will pull the base of this NPN transistor high when there is like 20 volts or something up there, and having this base here at some moderately high voltage, 1 volt, 2 volt or above, will pull this node low and turn off the series pass transistor. But anyway, let's ignore that for a second, because I don't think there is a problem with that. Now if you look at this resistor here, that's 10K, by the way, 10K. If you look at this resistor here in series with another Zener diode, a 10 volt Zener diode, that's just a reference. So this is a fairly classic, that's the easiest way to get a more or less stable reference here. You take some resistor, a Zener diode, and essentially if this is a 10 volt Zener diode, that node here is going to be around about 10 volts with respect to ground, you know, give or take. The problem with that is if you were to use this as a power supply without any of these transistors like that, so you might argue that you've got 10 volts here, great, so you use the 10 volts here as a power supply. As soon as you start to draw current, remember that the current has to go through this 10K resistor here, so there is going to be a massive voltage drop across this resistor, which means that you need small resistor values if you really want to do that here, and it also means that you need Zener diodes that are capable of dissipating that power. So in the end, you're wasting a lot of power. You know, if we're realistic about this, you just can't do it like that. So what you do is you take the current off and bypass it through a series pass transistor, which is done here in a fairly, it's not weird, it's not the most common thing, but you know, on the other hand, still, this is fairly common. These two transistors essentially ensure that you've got a voltage here that is about 0.6, 0.7 volts lower than what you feed into the base here. You know, I could emphasize on this a little bit. I mean, I already explained why you need a series pass transistor. Now, imagine you only had these NPN transistor here. You would feed the reference voltage into the base and connect your input voltage directly to the connector, the collector. That's a voltage follower. So that's just a very classic circuit that gives you an output voltage 0.6, 0.7 volts lower than whatever you apply to the base. Now that would work, however, because of the way the transistor amplifies current, at some point you need a considerable base current in order to allow for high collector currents. So what you could do there is you could add another transistor. This is called the Darlington Paradigm, and that would give you essentially the amplification factor, the gain of one transistor squared, but it would also double the voltage drop. And maybe in this case you don't want to do that, so you can use this. This has a name actually. I think it's a Zikli pair or something. I forgot the name of this transistor configuration, but anyway, it consists of an NPN transistor and a PNP transistor, and it only has 0.7 volts of drop. It's just one diode drop, but still allows you to let quite high currents pass through. So that's what's going on here. Now the bottom line of this is that in the end there is a beefy transistor up here. That is the series pass transistor, and a smaller transistor down here. And in fact, this is the one that has the hole, the blowout hole. So I think that what happened is this was shorted here, and there was quite a high current flowing through this series pass transistor here that just led the transistor to melt down. So what I'm going to do is I will take one more measurement. I will measure the voltage here before the transistor, because if I manage to get a stable voltage reading at this node here with respect to ground, even when the voltage drops to zero, as it did during the experiment we just did, it means that the problem clearly is somewhere in here. If the voltage here was dropping as well, then I'd have to look what I have, further upstream. So I just want to be sure that I have to focus on this part only. So I will do that. I think I'll do that off camera because I'm fairly confident that the problem is here and only here. And then I'll think about how to replace that transistor. Okay, so I checked what I just announced, and indeed the input voltage to this circuit is pretty much what I set on my power supply. This is very cool because essentially it means that there is nothing in between that can that could break. So essentially I have to fix this and hopefully I'm good. Surprisingly, there is a fuse along with some, inductors and shunt capacitors and stuff that are not very interesting and that for sure didn't fail here. But there is a fuse that did not pop, although the purpose of this fuse is probably to take care of exactly that case. Anyway, so how do I replace this transistor? There is several aspects to this question. The first one is how do I get it off? Now I can think of two ways. The first one is to use a hot air gun, and the second one is to use a soldering iron with a fairly large tip. I have a special tip that would allow me to cover all the 3 pins here of this SOT89 package. Although there is a bit of a problem because this package here, as far as I know at least, on the bottom side there is a pad that it's there for heat transfer. There is a reason they picked a larger transistor here, because it's supposed to conduct quite some current. So maybe for heat sinking, there is this pad on the bottom that is usually soldered down to the PCB. So even if I manage to heat up all the pins, I won't be able to get it off most likely. So I think I'll try with the hot air gun first. And then the question is also, what do I replace it with? And this is why it was important to discuss and understand how the circuit works, because that way I know that some characteristics of this transistor, for example the gain bandwidth product or whatever, are not so important, but I know that I have to pick a transistor that is able, that has a sufficiently high collector current, for example, a comparable gain to the transistor that they put in here, and things like that. So I will try to find a transistor that is suitable, and also I have to match the pin out. Obviously, I have to pick a transistor that has the same pin out. Unfortunately, today is Friday. I don't have time to do it today. So and tomorrow is Saturday, and I won't be able to buy parts tomorrow. So I think I'll check the basement and see whether I have anything suitable in here to replace this transistor with. So unfortunately I cannot do the desoldering in front of the camera because it's just, I mean, imagine you've got this massive hot air gun. In case you haven't seen that, by the way, I'm talking about a device like this. So the idea is to heat it up, maybe with a smaller nozzle, but anyway, to first heat it up maybe 100 degrees C, just to heat up the board, because there is quite some thermal mass in here. There is also components on the bottom on the other side of the board, and I don't want to heat it up so hot and long that these would fall off, obviously. So I will heat it up to 100 degrees C and then notch it up to 300, 350 maybe, and hopefully be able to lift up the transistor with a tweezer. Okay, so as you could see, this actually did work. I wasn't sure whether I really could catch it on camera, and probably the footage is not that great, but clearly it did work. So now the transistor is off. You can see that there is now exposed pads here. In particular, that large one I was referring to before. Removing this with a soldering iron, I could have done it, no problem, but still that was much easier. So I'm very happy that this did indeed work. Then looking at the transistors themselves, I'll also give you a high resolution magnified picture of that, because you don't see much here indeed, but that's the broken one. If I turn this around, again, there is this exposed pad here at the bottom, and that is my replacement that I could find in the basement. Fairly similar in terms of you know, like maximal collector current and stuff like that, breakdown voltage. So this shouldn't be a problem, and of course the pinout is the same. That's that's the most important thing. If the pinout is not the same, and I solder this on the board, then I'm screwed. So let me try to solder this. I won't film that because that's fairly straightforward, and hopefully this will work once the transistor is replaced. Okay, so I put the new transistor in place. That was super easy, so no big deal there. And I set up everything as I had it before to repeat that load measurement. And hopefully now, if I try to load down that power supply, the voltage will not drop anymore. So let me turn on the 12.5 volts supply voltage. And the first good thing here is that I'm indeed getting 9.5, 9.7 volts. So that's good. And now let me pull some current. I'm pulling 10 milliamps now, and I still have 9.5 volts. So that is great, because last time I did this check, the voltage dropped down to 0. So let me repeat that. And you can see that the voltage is dropping slightly, but clearly that's not a big deal. And I don't think that the remote head unit is pulling anything more than maybe 100 milliamps. So this is maintaining regulation just fine, no problem at all, and I'm very happy. So let's try and see if it works. Okay, so I'm going to be honest and tell you that I already played around with the unit quite a bit. I'm sorry that I couldn't catch that turn-on moment on camera where I realized that it actually did work and was fully functional. But anyway, here it is running. I've set it up such that on the left side there is this APRS thing going, which means that whenever it's receiving and successfully decoding a packet, like now for example, it's going to display that. There is another packet here from a German station. So this works here. That's actually fairly cool, because you're getting lots of packets, and that allows you to tell you something about propagation and whether the band is good or not at the moment. Anyway, here on the right side, I just set up a repeater. It's about 60 kilometers away. And it's interesting because this is a dual band repeater operating on 70 centimeters and 10 meter HF. So if we're lucky, we might get some remote stationing here while I'm talking. Great, so my message for this video essentially is as follows. If you've got a unit that is faulty, that is broken, that does not have a lot of value as it is right now, here you can hear the ID of the repeater anyway, then it's really well worth trying to repair it. And think about what it took me to repair this. At first, I needed a multimeter to take that voltage measurement, but multimeters are not that expensive, and this is a great investment anyway. So a multimeter to measure the voltage, and that already gave away that there was a short in that cable. And you know, maybe I could have been lucky and the short was the only problem. In this case it was not, but anyway, that would have been a very easy fix actually. And then I had to dig a bit deeper. I used the reload, my dummy load, to test the power supply, but to be honest, a resistor would have done just as well. So a bunch of resistors, a multimeter, and then once I figured out what was wrong, a soldering iron or a hot air station to extract the part. Now, the thing is that it maybe this looked a bit more difficult than it actually was, because first of all this discussion about circuitry, this is very important to me, but to be honest, I looked at the board and saw that there was something wrong with that transistor because it had the blowout hole and also the smoke stain on the chassis in the back. So that was a dead giveaway. And then in the end, maybe the trickiest part is to find a suitable replacement. If you want to be on the safe side, you just get exactly the same transistor. I just couldn't wait for Monday. Okay, that was just noise. But anyway, I couldn't wait for Monday, so I went for a similar transistor. But you don't have to do that. You can just buy exactly the same transistor. And then the last part is maybe the soldering. But again, I could have removed the whole PCB from the radio. I didn't want to do that because there is lots of power transistors of the finals and things screwed to that massive heatsink, and I would have had to remove all of those, and then there is thermal paste in the way and it gets a bit nasty, and so I preferred to extract it through that speaker hole. But there would have been ways to do it differently. So I think that with the help from the internet, to figure out whether the transistor is really broken and what a suitable replacement would be. This is not too hard to fix on your own. So all I can say is that I strongly encourage you to give it a try next time. And one last thing. In fact, what I showed you was pretty much exactly the steps that it took me to go forward in this repair. I didn't, cut out the parts that were red herrings or anything, and this also means that I did a couple of things wrong. For example, I should have resisted my urge to take everything apart and checked the cable at the very beginning. I did not, and there is lots of things that I just could have done differently. And that's what you get when you share the way you proceed. But still, I really hope that this is very interesting to you, and maybe there is one or two things that you can take from this. If not anything else, then the courage to try it on your own next time. So I really hope that was interesting. If you want to discuss anything, please do so in the comments. And I thank you for watching, and see you next time.